Hello, knowledge seekers. In this episode of 20-Minute Books, we delve into the cosmic realm with Stephen Hawking's iconic work, A Brief History of Time. This seminal book bridges the gap between the layperson and complex astronomical concepts, chronicling the fascinating history of the cosmos and contemporary breakthroughs in our understanding of the universe. Hawking, a renowned theoretical physicist, uncovers the mysteries of Big Bangs, black holes, and quantum mechanics, crafting a narrative that's accessible regardless of your scientific background. As we explore Hawking's insights, we realize his unique gift for making the intricacies of the universe not only comprehensible, but also engaging to all curious minds. A Brief History of Time is a journey through science's most profound discoveries, from the tiniest particles to the vastness of space and time. Stephen Hawking, who served as the Lucasian Professor of Mathematics at the University of Cambridge, was a legendary figure in scientific circles. His profound contributions, including the concept of Hawking radiation and the Penrose-Hawking theorems, have shaped our modern understanding of physics. As a recipient of the Presidential Medal of Freedom and a lifetime member of the Pontifical Academy of Sciences, Hawking's work has left an indelible mark on both science and popular culture. This book is for those who have ever gazed at the night sky in wonder, questioned the origins of the universe, or sought a clearer understanding of the complex world of quantum mechanics and black hole dynamics. Join us as we squeeze the vastness of cosmic history into a 20-minute odyssey. A Brief History of Time, From the Big Bang to Black Holes. Introduction. Embark on an astronomical journey of discovery. When you look up at the night sky, you're not just admiring beauty, but also looking back in time to the very origins of the universe. The twinkling stars invite us to unravel the grand design of space and answer some of humanity's oldest questions. A Brief History of Time is a compass through this cosmic journey, a book that deciphers the universe's complex language into one we can all understand. Within its pages, you'll explore the fundamental principles that sculpt our universe, the laws that reveal its past, shape its present, and predict its future. It's an exploration that's not just for astrophysicists or those with a penchant for equations. Instead, it's a narrative crafted for anyone with curiosity about the vast expanse above us. Prepare to delve into the enigma of black holes, celestial powerhouses that bend the rules of physics and challenge our understanding of reality. Discover not just their awe-inspiring might, but also the loopholes they present, teasing at the possibilities that lie at the edge of our scientific grasp. But that's not the only mystery that awaits. This book peels back the layers of time itself, addressing head-on the velocity of its passage, and dissecting the evidence that assures us it marches forward, not backward. As you immerse in these themes, you're guaranteed an altered perspective. The starry night sky will no longer be just a canvas of light, but a map to the universe's deepest riddles, riddles that A Brief History of Time will help you begin to solve. After this expedition through its pages, the cosmos will open up to you in ways you've never imagined. Part 1. Grasping the Foundations. The Vital Role of Scientific Theories. Have you ever gazed out at the stars and wondered about the gravity that keeps them in place, or contemplated the laws that give structure to time and space? Behind these vast celestial mechanics are theories, the scientific frameworks that allow us to decode the universe's behavior. A theory is much like a map for navigating through a complex terrain of empirical observations. It's more than just a speculation. It's a coherent explanation that aligns disparate pieces of data into an understandable and predictive pattern. Take, for example, Isaac Newton's legendary apple inspiration that led to the theory of gravity. This wasn't just about fruit and foliage. It was about the very tether that holds planets in orbit and governs the motion of cosmic bodies. The power of a theory is twofold. Firstly, it's predictive. With Newton's principles, we can calculate where a planet like Mars will be positioned in the cosmos 6 months from now with astonishing accuracy. It's the crystal ball of science, providing foresights into celestial movements. Secondly, and just as crucially, theories are eternally on trial. They stand before the court of evidence, always ready to be challenged, always precarious. They are mutable. This is their strength. The geocentric model where Earth sat at the universe's heart was once widely accepted. However, it crumbled when Galileo's observations of Jupiter's moons provided clear evidence of celestial bodies orbiting something other than Earth. This quality of theories, that they can always be disproved by new discoveries, ensures that science never stagnates. It is a remarkable feature of the scientific method that no matter how established a theory might seem, it's never immune to revision or replacement if new insights emerge. In this way, science is always a work in progress, constantly refining its depiction of reality as it marches in tandem with time. Part 2. Newton's timeless laws, changing our perception of motion forever. Long before the advent of modern scientific thinking, stillness was misinterpreted as nature's default. The belief was that an object at rest would remain so unless an external force coerced it into action. However, in the 1600s, Isaac Newton upended this notion and set the stage for a revolution in physics. Newton's keen observations and intellectual rigor led to the realization that motion, not stillness, was the cosmic norm. The celestial dance of planets around stars and the grand rotation of galaxies served as his evidence. Everywhere he looked in the universe, movement was perpetual. To articulate this relentless motion, Newton introduced 3 foundational laws. The first law challenges the misconception of natural rest by proposing that an object will maintain its course and velocity unless an external force intervenes. Inspiring this was Galileo's simple yet groundbreaking experiment with rolling balls, illustrating that they travel in unwavering lines when gravity is their sole influencer. Newton's second law offers an equation of motion. Force equals mass times acceleration. In a more relatable context, consider 2 cars of equal power. The heavier one will inevitably accelerate more sluggishly, showcasing the law's prescience in everyday phenomena. The third, and arguably the most celebrated of Newton's laws, addresses the universal force of gravity. His proposition was radical. Every object in the universe exerts an attractive force upon every other object, a force directly tied to their masses. This revelation accounts for everything from the simplest act of picking up an apple to the complex orbital mechanics of planetary systems. These laws, born of Newton's revolutionary insight, redefined our understanding of the cosmos. They established that movement is not just a passing curiosity, but the very essence of all existence in our universe. Newton changed our worldview, revealing an intricately balletic universe governed by motion and balance. Part 3. The steadfast speed of light. A contradiction in the relativity of speed. Newton's vision of the universe introduced us to the relative nature of motion, where how fast you are going always depends on your point of reference. This was a significant leap forward as it divorced the concept of motion from any fixed backdrop, placing it squarely in the realm of perspective. Consider a train gliding along the tracks at a swift 100 miles per hour. To a bystander on the platform, you, absorbed in your book inside the train, are racing by at that speed. But within your cozy, moving compartment, you might as well be motionless as far as the book in your hands is concerned. However, when it came to the speed of light, Newton's ideas met a conundrum they couldn't illuminate. The speed of light defies this rule of relativity. Radiating through space at a consistent 186,000 miles per second, it remains steadfast, wholly indifferent to the motion of the observer or the source of light. So if you were to chase a beam of light on that 100 miles per hour train, it would speed away from you at the same rate as it would if you stood still on a platform. It was a glaring inconsistency in the fabric of Newtonian physics, a rip that couldn't be mended within its existing framework. It wasn't until Albert Einstein stepped onto the scene that the rip became a gateway to a deeper understanding of the universe. With his theory of relativity, Einstein provided profound answers to this conundrum, reshaping our understanding of space, time, and the very fabric of reality. How can an unchanging speed of light coexist with the relative nature of motion? Einstein's insights would bridge this gap and lead to some of the most groundbreaking revelations in physics. Part 4. Relativity unfolds, challenging the absoluteness of time. Albert Einstein's discovery of relativity dramatically shifted our view of physics, presenting a predicament for those adhered to Newtonian mechanics. The constant speed of light didn't fit snugly within a universe where speed shifted according to an observer's relative motion. Hence, Einstein proposed a novel framework to reconcile this inconsistency. At the bedrock of Einstein's theory of relativity is a seemingly simple assertion: the fundamental laws of physics hold true for everyone, regardless of their speed. This means that even as observers travel at different velocities, they all witness light's velocity as a constant, unyielding at 186,000 miles per second. Grasping this leads to a startling revelation, one that overturns centuries of belief: time is not a universal constant. This notion shakes the very foundations of how we perceive events unfolding in the cosmos. Because the speed of light remains fixed for all observers, those moving relative to each other will perceive time differently for the same occurrence. Let's picture two observers, one approaching a beam of light and another moving rapidly away from it. Although their speeds differ, the light's velocity remains unaltered in both their perspectives. This leads to each observer experiencing the event, say the pulse of light flickering, at what seems like different times. It's the relativity of simultaneity in raw display. By measuring the interval traversed over a fixed speed, that of light, they end up with divergent, yet equally true interpretations of time. Were they to compare notes, their clocks would tell corresponding tales of two distinct moments for the very same flash of light. Within this new paradigm, neither observer possesses a more legitimate account of time. Each perspective is uniquely accurate. Einstein's relativity doesn't just redefine our understanding of space and time, it amalgamates them, compelling us to acknowledge that time is not universally experienced, but intimately tied to the observer's frame of reference. Part 5. Quantum states and the puzzle of particle behavior. The subatomic realm operates by rules that frequently confound our everyday understanding of the physical world. When scientists set out to examine particles like electrons or photons, the components that construct matter, they encounter a baffling phenomenon. The more precise the measurement of a particle's position, the more elusive its speed becomes, and vice versa. This uncanny principle, unearthed in the Roaring Twenties, was dubbed the uncertainty principle. Faced with this predicament, physicists had to devise a new approach, shifting their gaze from exactitudes to probabilities. This is where the concept of a particle's quantum state takes the stage. A quantum state is like a cloud of possibilities, charting a spectrum of probable locations and velocities for a particle at any given moment. Since sharp precision eludes measurement, physicists track a particle by considering all the potential points it might inhabit and the array of speeds it could possess. As the particle weaves through space-time, it's as though it scans through these possibilities, selecting its next move. To uncover the particle's likely whereabouts, scientists treat it analogously to a wave. Picture a tremulous string, ebbing and flowing with crests and troughs. A particle resonates much like that, with its pathway illustrated as a mosaic of overlapping, dynamic waves. To determine where a particle is most apt to be found, scientists juxtapose these waves. At points where the wave peaks and troughs align, that's where the particle has the highest probability of being detected, a phenomenon known as interference. Conversely, places where the waves are out of sync represent the least probable locations. Hence, the wave's interference patterns become a map of likelihood, a navigational tool for predicting a particle's path through the quantum fog. This approach to particle behavior brushes aside certainty in favor of a more nuanced, probabilistic comprehension of the microscopic universe. Part 6. Space-time and the curvature that defines gravity. As you engage with the world, you experience life's dimensions in terms of height, width, and depth. Yet, there's a less tangible but equally vital dimension intertwined with these: time. Together, these four dimensions forge the fabric known as space-time, a conceptual framework that physics uses to describe the events in the cosmos. An event in this four-dimensional universe is characterized not just by where it happens, but also by when. By adding time as the fourth coordinate, scientists attain a complete picture, crucial for calculations, because as the theory of relativity has shown us, time bends to the relative speeds of observers. Now, what is truly fascinating about the merger of space and time is its profound effect on our understanding of gravity. Through space-time, gravity is unveiled not as a mere force, but as a geomorphic feature of the universe, a curvature shaped by mass. Envision space-time as a taut blanket hovering. Place a weighty object, such as a densely packed sphere representing the sun, at its center, and watch the fabric warp under its influence. This is the essence of gravity. It's the dents and hollows in space-time authored by celestial bodies. Other objects traverse these indents created in the space-time continuum. In doing so, they're simply following the most direct path between points in space-time, often resulting in circular orbits around larger masses. This path is not a choice, but the path of least resistance, a natural consequence of the space-time curvature. Let's return to the blanket analogy. An orange resting on the fabric creates a significant well, a distortion of the blanket's flatness. If you were to roll a marble nearby, it would naturally veer towards and orbit the orange, propelled by the fabric's curves. This is a picture of how gravity operates, not a force that pulls, but a curve that guides. Space-time and its warps underpin the gravitational ballet we witness every time we peer up at the orbital movements of stars and planets. Part 7. From stellar giant to cosmic enigma, the birth of a black hole. The life cycle of a star is a narrative of intense energy, a tale of radiance that sustains celestial light and warmth. Nevertheless, even stars are mortal, and their eventual demise is a harbinger of profound transformation. For the stars of colossal magnitude, death is the precursor to one of the universe's greatest mysteries, the emergence of a black hole. A black hole's inception is rooted in the formidable gravitational force of a massive star. Throughout its life, the star fends off gravitational collapse by fueling itself with nuclear reactions. But once its reserves deplete, the star can no longer resist the crush of its own gravity. In a dramatic final act, it implodes into an infinitesimal point of endless density known as the singularity. This singularity, veiled at the heart of the black hole, is where space-time is pulled into an incomprehensible curvature. The gravitational pitch is so severe that nothing, not even light, can break free once it dances too close. Surrounding the singularity is the black hole's shadowy threshold, the event horizon. Anything passing this border is inextricably drawn inward, forever enshrouded in the abyss beyond which even light cannot escape. It earns the black hole its moniker, an astronomical phantom swallowing all signs of existence. How then can we detect these dark objects in the vastness of space? Scientists look for the telltale gravitational effects black holes speak in, the distortions in orbits, and the radiation of X-rays erupting from the heated maelstrom of material being devoured. This cosmic drama unfolds near black holes, where stars are caught in their gravity, circling menacingly close. Another method is to observe the radio and infrared signals emanating from regions we suspect a black hole presides. At the very core of our Milky Way, there lurks a source emitting these waves, suggesting a supermassive black hole reigning from within. an invisible sovereign dictating the dance of stars and cosmic dust. Part 8, a paradox solved, black holes and the surprising escape of radiation. Black holes, with their immense gravitational grasp, seemingly defy the very possibility of escape for anything that dares too close a pass. It stands to reason, then, that if even light is ensnared beyond the event horizon, surely nothing else could break free. However, the landscape of astrophysics is riddled with surprises, and black holes are no exception. Here's where the laws of thermodynamics orchestrate an unexpected twist. Specifically, the second law of thermodynamics posits that with the increase of entropy, a measure of disorder, there must also be an increase in temperature, which further necessitates the release of heat. Just as a heated poker glows and radiates in the aftermath of a flame's touch, black holes too, it turns out, must find a way to balance the books of entropy. This balance is made possible by the presence of virtual particle pairs near the event horizon, existing momentarily at the cusp of the abyss. These virtual particles include one with positive energy and another harboring negative energy. Despite their intangibility, their impact on physical laws can be witnessed. In the mighty grip of a black hole's gravity, the negative energy particle can fall into the void, bestowing upon its positive energy twin the vital boost required to catapult it out into the cosmos. The result? The black hole emits thermal radiation, preserving the sanctity of the second law of thermodynamics. This delicate dance isn't without consequence for the black hole. The negative particles absorbed by the black hole slightly diminish its mass, a cosmic tithe paid to the universe. Over unimaginable spans of time, this can lead to a black hole's gradual dissipation and eventual evaporation. As its mass shrinks into insignificance, we can even fathom a dramatic climax, an explosion of energy on par with millions of hydrogen bombs, a cosmic finale befitting the enigma of a black hole. Part 9. Unraveling the direction of time's relentless march. The notion that time could one day reverse and send us hurtling back through history is a tantalizing, albeit disconcerting, idea. While the prospect of time travel captivates our imagination, current scientific understanding offers compelling evidence that the arrow of time is firmly set towards the future. Three particular avenues of scientific inquiry reinforce our understanding of time's forward trajectory. The first is the thermodynamic arrow of time, a concept deeply intertwined with entropy. According to thermodynamic principles, entropy, or the measure of a system's disorder, naturally increases over time in a closed system. This idea is etched into our understanding of the universe, from broken cups scattered on the floor to the very stars burning out in the sky. These are irreversible processes that imprint upon us the irreversible flow of time. The second indicator lies within our own minds, the psychological arrow of time. It is stitched into our memories, the way we perennially perceive the past as a record of decaying order. We remember the cup whole upon the table, but cannot premember its shattered future. Our memory serves as testimony that time proceeds in one direction. Lastly, we reflect upon the cosmological arrow of time, which is the universe's ongoing expansion since the Big Bang. In unison with the thermodynamic arrow, the universe's growth suggests that as it unfurls, entropy escalates. Should the universe reach a zenith of disorder and begin to contract, theoretically reversing the cosmological arrow, it would contradict our ability to experience time. Intelligence, and life as we recognize it, depends on entropy to fuel the processes that sustain us. In essence, as long as sentient beings thrive in an expanding universe, drawing energy from the increase of disorder, we're bound to perceive time as moving inexorably forward. These strong indicators, rooted in thermodynamics, psychology, and cosmology, anchor our experience of time to a single onward direction, shaping the fundamental backdrop of existence as we comprehend it. Part 10. The Quartet of Forces Orchestrating the Cosmic Dance. The grand tapestry of the universe is woven with forces that sculpt and sustain the myriad forms and phenomena we witness. While gravity is the most familiar force, whispering through the falling leaves and chaining planets to their stars, it's merely one of four fundamental forces that govern all interactions in the cosmos. Indeed, alongside gravity thrives the force of electromagnetism. One witnesses the electromagnetic force in the simple clinging of a fridge magnet, or in the invisible energies that charge a cell phone. It acts upon particles with electric charges, such as electrons and quarks, with the ability to both attract and repel. In the microcosmic world of atoms, it is the electromagnetic force that beckons electrons to dance around their nuclear partners. Complementing this is the weak nuclear force, an elusive power that influences every particle that makes up matter, its claim to fame being the phenomenon of radioactivity. Termed weak, due to its limited range, it nevertheless gains in strength proportionately with energy, inching closer to the might of electromagnetism at high energy levels. Strong nuclear force is another cornerstone of universal interactions. It's the relentless force that glues protons and neutrons within an atom's nucleus, and further unites the quarks that compose these subatomic particles. The interesting nuance with strong nuclear force is its inverse relationship with energy. Unlike its peers, it dwindles as energy escalates. At the zenith of energies, when the scales tilt and the forces converge in strength, lies the grand unification energy. It is at this exalted state that electromagnetic, weak nuclear, and strong nuclear forces shed their individual masks, uniting as divergent expressions of a singular force. This unified force, though a subject of theoretical pursuit, is conjectured to have played a defining role in the universe's inception, possibly dictating the very moment of its fiery birth. Was Part 11. The Enigmatic Origins, piecing together the puzzle of the Big Bang. The genesis of the universe is a mystery nestled deep within the fabric of space-time, a cosmic riddle that scientists continue to unravel. The prevailing consensus among the scientific community is that the universe's clock started ticking with the Big Bang, a cataclysmic moment that birthed an ever-expanding cosmos from a point of infinite density and heat. Yet the precise mechanisms underlying this event remain shrouded in scientific conjecture. Among the theories striving to elucidate the dawn of existence, the hot Big Bang model has garnered significant support. According to this model, the beginning of everything was a singularity of zero size, a point where the concepts of space and temperature lose their conventional meaning. During the Big Bang, the universe unfurled, and as its volume grew, its scalding heat diffused. Within those primordial moments, the very elements that now fill the periodic table were forged. Gravity, the gentle architect, took hold of denser regions of this expanse, spurring the creation of galaxies. Within these swirling, nascent structures, clouds of hydrogen and helium collapsed under their own weight, triggering nuclear fusions that birthed the first stars. Meanwhile, dying stars' last breaths were monumental, seeding space with the raw ingredients for new stars and planets. Though the hot Big Bang model holds sway, it's not alone on the theoretical stage. Enter the inflationary model, a narrative that speaks of an infant universe so brimming with energy that the three fundamental forces, strong nuclear, weak nuclear, and electromagnetic, stood united in strength. This embryonic state was brief, and as the universe burgeoned, these forces lost their symmetry, each adopting distinct intensities in a fleeting moment. The partitioning of these forces released energy on an unimaginable scale, with a curious anti-gravity effect that propelled the universe to swell at an accelerating pace. Both models, differing in their specifics, converge on a grand scene of an evolving universe, one that continues to captivate and challenge our understanding of time, space, and the very nature of existence. Part 12. the quest for a grand unified theory, bridging the realms of relativity and quantum mechanics. Scientists navigate the universe through the lens of two phenomenal but seemingly incompatible theories. General relativity is the sovereign of the celestial, painting the cosmos with the broad strokes of gravity's influence. Contrastingly, quantum mechanics is the master of the minute, detailing the world of particles smaller than atoms with finesse. Yet the aspirations to thread these theories into a single tapestry, a unified theory of everything, have encountered fundamental hurdles. The schism between the large-scale predictions of general relativity and the minute workings of quantum physics forms a deep chasm in our scientific understanding. One significant obstacle lies in the tendency of quantum physics equations to produce infinite outcomes, values that contradict the tangible finitudes observed in our universe. Space-time curvature, according to quantum predictions, spirals towards infinity, a reality that simply does not resonate with astronomical observations. In an attempt to rectify these infinities, scientists introduce counter-infinities, a practice that ultimately derails precise predictions, leaving physicists to retrofit reality into the equations instead of the other way around. Furthermore, quantum theory posits that the vacuum of space is teeming with virtual particle-antiparticle pairs, invisible yet measurable in their effects. Herein lies another contention with general relativity. With space being boundless, the energy of these virtual pairs would amount to infinity. However, with energy and mass being interchangeable as per Einstein's E equals sign mc2, this would assign infinite mass to these virtual entities. This proposition would render the universe gravitationally unstable, succumbing to an insurmountable gravitational pull and destining everything to collapse into a singular black hole, a scenario in stark contradiction to the expanding cosmos we observe. Thus, the marriage of general relativity and quantum mechanics remains one of the most profound challenges in modern physics. It's a puzzle that has stumped the brightest minds, a Gordian knot at the heart of our pursuit of the ultimate understanding of the universe's machinery. Final summary. The cosmos, with its whirl of complexities and enigmatic phenomena, may often seem beyond the grasp of our daily understanding. Physics, as the language of the universe, does indeed weave intricate patterns of equations and hypotheses that can intimidate even the curious mind. However, the complexity of physics conceals profound simplicities, fundamental principles that demystify the universe's grandeur. Armed with key rules and laws, anyone can embark on a journey of cosmic exploration. These guiding principles serve as beacons, illuminating the vast and varied machinations of space and time, gravity and light, energy and matter. By unraveling the foundational tenets of the universe, the seemingly arcane suddenly becomes accessible, and the celestial sphere transforms from a distant enigma into a familiar expanse ripe for discovery. Embracing this knowledge doesn't require a specialization in astrophysics, but an open mind and a desire to understand the forces that shape our existence. With these insights, the universe reveals itself not as a series of impenetrable secrets, but as a fascinating narrative waiting to be comprehended and appreciated. In this newfound light, every star, planet, and galaxy becomes a character in an ongoing story, a story where you, the observer, play a crucial role in deciphering its plot. The universe is a treasure trove of wonders, and with the keys of physics in hand, its treasures are yours to unearth. Thank you for joining me today on this journey of learning and discovery as we explored the insights of another thought-provoking book in our growing library of knowledge. If you've enjoyed our time together, please take a moment to follow our podcast, give us a 5-star rating, and share 20-minute books with other knowledge seekers. Your support truly means a lot. Don't forget to join me again in the next episode, where we will delve into another enriching book. Until then, happy reading and happy listening.